Dear students, in today's session, I am going to explain about a topic concept called optical instruments. Now, this is the last session of this particular chapter, ray optics. So, all the remaining numericals I am going to complete in this particular session. The first optical instrument which we are going to study is a simple microscope. Simple microscope is also called as a magnifier. So, if you remember in the experiment related to the travelling microscope in our laboratory, so you all have used one small lens to see the readings, that is main scale reading and vernier scale reading. That single small lens which we are using is a simple microscope. Or if you take a single lens which is used to magnify, to read your hand in a palmistry, correct? So, they use a single lens. So, that also it acts like a simple microscope. So, any single convex lens which is used to get a large image of an object is called as a magnifier, or it is also called as a simple microscope. So, what kind of question that will appear in this particular topic? So, ray diagram. So, you have to study all the ray diagrams related to these instruments. Now, the first ray diagram, so related to the simple microscope is here. Now, this is the magnifier, single convex lens. We use an object in front of it. Take a magnifier, single lens, and place an object. So, that object must be placed very close. So, what do you mean by very close? So, we have to place that object between the optic center and the principal focus, optic center and the principal focus, so that OB acts as the object distance. So, therefore, that object must be placed always within the principal focus or within the distance or lesser than distance of the focal length, because from here till here it is a focal length. So, that is a focal length. Now, for the formation of the image, we are going to consider two rays. Ray number 1, which is here from the object, AB is the object. You consider a ray which is parallel to the principal axis, and once it is parallel to the principal axis, it passes through the principal focus. Somewhere here it passes through the principal focus. You take one more ray passing through the optic center, that passes straight without any deviation, undeviated. So, therefore, the kind of the rays that we get here are diverging. So, they do not form any image this side. So, extend it backward, which is imaginary, and then these rays now they appear to diverge from this particular point. So, that is why we get an image corresponding to A, we get A dash, corresponding to B, we get B dash. So, that this is the image that we get. So, for an object we get an image. So, where we have to form the image? We have to form the image at a distance D. This is the image distance, V is equal to D. What is that D called? D is called the least distance of distinct vision. So, if you hold an object in front of your eyes, correct, you cannot see the image of it properly, or you have to strain your eyes, correct. So, to see that image correctly or to get a clear image on the retina, the distance between your eyes and the object should be 25 centimeter. So, that is called least distance of distinct vision, and that particular point is also called as a near point. So, the object has to be placed, now the object, that is position of the object I am talking about. So, the object has to be placed at least at a minimum distance of 25 centimeter. So, therefore, we are going to form an image at a distance of, here in this case the object is placed very close to the lens, but its image will be formed at the least distance of distinct vision, and that value of the capital D for normal eye is equal to 25 centimeter. So, therefore, this is the ray diagram of a simple microscope. And for every optical instrument, we define a term called magnifying power. What is its ability to magnify an image, okay, which we normally refer it as optical zoom in normal cameras. So there is 2x, 5x, 1.5x, 0.5x, that zoom is there, correct? Now, so that optical zoom which we are talking about is nothing but the magnifying power. So which is given by the equation 1 plus d by f, where f is the focal length of the lens and d is that least distance of distinct vision, and m is the magnifying power of the lens when the image is formed at what we call near point. Near point is this 25 centimeter. You can form the image even at far point. Far point means infinity, where the focal length, magnifying power is given by d by f only. There's no, so here it's 1 plus d by f, here it is d by f. So this is the magnifying power of a simple microscope. So simple microscope is also called as a magnifier, and this is the ray diagram for it. The object must be placed between O and F, and the image will be formed at least distance of distinct vision. And you can very clearly see the height, here this is the height of the object and this will be the height of the image. You will get always a enlarged image when viewed through, see, we view through the lens. So image will be formed on the other side, whereas the eye or the observer should be on exactly the opposite side of the object. Now, to get more magnification, this one single lens is not enough, okay, for more magnification, correct. So one lens is not enough. So we take more lenses, multiple lenses, at least a minimum 2 lenses. Now what is the advantage of using the 2 lenses? Yesterday I have told you that whenever we combine lenses, magnification is get multiplied, correct? Magnification is get multiplied. So that's why for higher magnification we go for combination of the lenses. So in simple microscope we use only one single lens. You can't get very high magnification because there is a limit for the focal length. So to get more magnification we use the 2 lenses, and such such instrument, optical instrument, is called a compound microscope. The travelling microscope which I have used in the physics lab is a compound microscope. The microscope used in the biology lab, correct? So to get higher magnification is also a compound microscope. So therefore in compound microscope minimum we use 2 lenses. So what is the ray diagram of such lenses? So let's see. So this is the ray diagram for compound microscope, where you can see there are 2 lenses are used. 2 lenses are used. The first lens is called as objective. The other lens is called as eyepiece. So if you remember the travelling microscope, okay, so where this is the lens through which we view, and this is the lens which is used to focus an object. So therefore this is the objective lens. So this is the eyepiece in travelling microscope. So if you see the aperture or the size of the lens, objective is of small aperture, objective, whereas eyepiece is of large aperture. So that's the difference in terms of the size. Objective is of small aperture and eyepiece is of large aperture. And we can always adjust the objective as well as the eyepiece, the distance between them can be adjusted, so that the object which we place is adjusted or is placed slightly beyond the principal focus of the object. In simple microscope the object is placed within F, but here it is placed slightly beyond F. See, the optic center is here. So this is the optic center of the first lens. This is the principal focus of the first lens. So object is adjusted beyond the, so that UO becomes the object distance for the objective. UO is the object distance for the objective, and FO is the focal length of the objective. Capital FO is the principal focus, small FO is the focal length of the objective. So we are going to again consider two rays. The ray number 1 parallel to the principal axis, it passes through the principal focus and then it is get refracted. The second ray, which is allowed to incident, it is allowed to pass through the optic center. Since it is a thin lens, it passes straight without any deviation. And what we get to see here is these two rays, after the refraction, they meet at a particular point here. And that particular point is nothing but the image corresponding to A. So for real object, we get a real image. By the way, in the case of a simple microscope, what is the nature of the image? It's a virtual because it forms behind the lens. Virtual image, enlarged image and erect image. Virtual, enlarged and then erect image. All virtual images are erect in nature. Okay. Now here we get an object and then corresponding to this we get the real image. So what is that nature of the image which we get? A dash B dash. It's a real and then inverted and then enlarged. So AB is like this. This is AB and this is A dash and B dash. Okay, so we'll write here this is A dash AB, A dash B dash. So this is the kind of image that we get. This is B dash, this is A dash. So real, inverted and enlarged image we get. Okay. So now what we do is, there is an eyepiece. So eyepiece is adjusted in such a way that, see this is the optic center of the eyepiece. That image which is formed, now it acts as object for the eyepiece. It acts as object for the eyepiece. A dash B dash is the image for the objective, but it acts as object for the eyepiece, and it is adjusted, its position is adjusted so that it lies within the principal focus of the eyepiece. So this is FE, see, it's placed between C2 and FE. It's adjusted within, not beyond, it's within. Here it is adjusted beyond the principal focus. It's adjusted within. And then these two rays, which are converged here, you make them to fall on the lens, then it undergoes a refraction. What kind of refraction? The rays which are falling here, they diverge. We have seen that, in the case of a simple microscope, whenever the object is placed within the principal focus, after the refraction, the rays, they diverge, and then to form the image, we extend the rays backward, and the same thing we have to do it. So here we have one ray, we have two, we have three, they diverge, and when you extend them backward, corresponding to A dash, we get A double dash here, like this. This is A double dash, and this is B double dash. Okay, so we get one more image. So A double dash, B double dash is the image for the eyepiece. So let me repeat, AB is the object for the objective, and its image is A dash, B dash. Now for the eyepiece, A dash, B dash is the object, and its image is A double dash, B double dash, which is here. You compare the image with respect to this. If you compare the image with respect to this image is virtual, it's erect and enlarged with respect to this, because both are in the same direction, correct? So it's a virtual, it's enlarged, and then it is erect. But we always find the nature of the image with respect to the object, the real object, which is this. So I have to compare with respect to this. So now when I compare with respect to this, we find that the image is virtual. This is up and this is down. So that means the image is inverted and image is enlarged. So we get virtual, inverted, enlarged image using the compound microscope. What is the formula for the magnification? So the magnification is given by L by F O, and then we have L is the length here. L is the length, or it's the distance between the objective and the eyepiece, and then we have it's D by F E. So equation, let me check. It's yes, fine. So this is the magnification. M is equal to L by F naught and D by F E. FO and FE are the focal length of the objective and focal length of the eyepiece. L is the distance between the objective and the eyepiece, and D is the least distance of distinct vision at which we form the final image. Here it is. Okay. So this is the expression for magnifying power of a compound microscope, and then we have two lenses are used, objective lens and eyepiece lens, and objective lens is of less aperture, whereas eyepiece is of more aperture. The next optical instrument is a telescope. So what is a microscope? Microscope is an optical instrument which is used to view enlarged image of nearby object. What is a telescope? Telescope is an optical instrument which is used to view enlarged image of far object. And we are going to learn one of the telescope, which is astronomical telescope. Telescopes are of two types. One, astronomical telescope, and other is the terrestrial telescope. Astronomical telescopes are used to view enlarged image of far object, which is celestial object or objects which appear in space, and the other is used to view distant object on the surface of the earth. So this is called terrestrial telescope. Okay. So binocular acts like terrestrial telescope. So this is the ray diagram for astronomical telescope. Whenever we use a telescope, the object will be at very large distance. It can be stars, it can be planets, comets. So the kind of the ray that we get from the celestial object is a parallel beam. So again, there are two lenses are there, objective lens and the eyepiece. In this case, the aperture of the objective is larger compared to the eyepiece. Objective is of large aperture compared to the eyepiece. So here we get a parallel beam on the objective, and it's get converge at a particular point. So we get real image, and then we get enlarged image. Okay. So real and inverted, and then we get enlarged image. Real, inverted and enlarged, which is here AB, and that is formed at the principal focus of the objective. Now the position of the eyepiece is adjusted in such a way that the focal length of the objective and the focal length of the eyepiece, they coincide, and whenever the object is placed at the principal focus, the final image what we get will be at infinity. So, object will be at infinity, image also will be formed at infinity. So, you can see the rays which are falling here, they are all parallel to each other. The refraction in such a way that we don't get a divergent beam, we don't get a convergent beam, but we get a parallel beam, which clearly indicates that when you extend the rays backward, the final image will be formed at infinity, and which we can view through the eyepiece. So, therefore, in microscope, the image will be formed at the near point, whereas in telescope, the final image will be formed at infinity, that is called at far point. Now, what is the magnifying power of the lens? Okay, by the way, what kind of image do we get here? So, we get the virtual image because it is on the same side. So, this is the image formed by the objective, and that image formed, it acts as object for the eyepiece. So, that the final image will be virtual and it is inverted and then enlarged, similar to the compound microscope. So, therefore, the nature of the image is same in compound microscope as well as in the case of a telescope, that is a terrestrial, not the terrestrial, astronomical telescope. So, what is the formula for magnifying power? The magnifying power is ratio of focal length of the objective to the focal length of the eyepiece, because if focal length of the objective is always larger compared to the focal length of the eyepiece. So, it is FO by FE, and the length of the instrument is FO plus FE. The sum of the focal length of the objective and the focal length of the eyepiece. So, when you add, you will get the length of the telescope. So, therefore, the length of the telescope depends on the focal length of the objective and the focal length of the eyepiece. So, this is the next instrument, which is astronomical telescope. Nature of the image is virtual, and then it is inverted, and then it is enlarged. So, we have one more telescope which is based on the principle of reflection and refraction, okay, which is called as it is designed by Cassegrain. So, that is why it is called as a Cassegrainian telescope, where we use a huge mirror. So, this is a mirror here, concave mirror, having opening at its center. So, that is a concave mirror. Then we use a convex mirror here, and then finally we use a lens. So, this is a reflecting type of telescope. What we have studied earlier, that is a simple microscope or compound microscope or even the telescope, is a refracting type of telescope where we use only lenses. But in reflecting type of telescope, mainly we use a mirror, but to view the object, finally we use a lens. So, here parallel beam from a distant object falls on the mirror. So, this is the mirror here, falls on the mirror, is get reflected, see, is get reflected like this, and again it falls on the convex mirror, which acts as a secondary mirror. Objective mirror is the primary mirror, this is the secondary mirror. The rays again they get reflected, and then they get focused at a particular point, and that is how we can see the image through the eyepiece of the Cassegrainian telescope. So, Cassegrainian telescope is a reflecting type of telescope in which we use a mirror and a lens. So, mainly mirror, because it works on the principle of reflection, Right. So, let us solve a numerical based related to the refraction. An object of size 3 centimeter. So, height of the object is given 3 centimeter, is placed 14 centimeter in front of a concave lens. So, there is a concave lens, an object is placed in front of it. So, this is the optic center, and when we measure the object distance, it is opposite to the incident ray. So, sign is negative. So, u is minus 14 centimeter. In front of a concave lens, so focal length is negative, minus 21 centimeter. Focal length is negative for a concave lens. Calculate the position and size of the image. So, you have to find the position means a V, and we have to find hi, height of the image. Now, the relation between the height of the image is given by magnification is always height of the image to the height of the object, which is also equal to the ratio of the image distance to the object distance. That is equal to f minus v, f minus v by f, and that is also equal to f by f plus u. So, this is the formula that relates the height of the image, height of the object, object distance, image distance, and focal length. Now, here u and f is given. U and f is given. So, from that we can find the value of v. So, to find v, I can use lens maker's formula. 1 by f is equal to minus 1 by u plus 1 by v. That is minus 1 by f is 21 minus 21. That is why it is minus here, and u is also minus. So, minus of minus becomes a plus here. So, plus 1 by 14 is equal to 1 by v, and to simplify that I will retain 1 by v. So, 1 by v is equal to, I will get minus 1 by 21 minus 1 by 14. So, here so common 21 into 14. So, that is minus 14 here and minus 21, which is minus 20, 30, 34, 35, minus 35 by 21 into 14. So, it is a multiple of 7. So, here we have 7 2s are, and then this is 7 5. So, therefore, we get v is equal to 1 by v is this much. So, v is equal to 21 into 2 is 42 by 5 with a minus sign. So, we can divide that. That is equal to minus 8. 5 8s are 40, 20 means it is 5 4. So, minus 8.4 centimeter is the answer, and negative sign again indicates that the image is virtual. Okay, it is on the same side we get. So, it is a virtual image. Okay. Then we need to find the now height of the image. So, I will use this relation. Height of the image we need to find hi, and ho, height of the object, is given 3 centimeter. That is equal to, image is here minus 8.4 by object distance is here minus 14. So, height of the image is minus 8.4 into 3 by minus 14. That minus of minus becomes plus, and we can simplify that. 8.4 into 3 divided by 14. So, that will be 1.8 centimeter. So, height of the object is 3 centimeter, height of the image is 1.8 centimeter, which is a diminished image that we get. So, we have completed this topic. Again, all the numericals are also completed. So, again, as I mentioned earlier, if you have any doubts, you can message me. I will clarify doubts related to any of the topic. Okay. So, concentrate on the questions that have appeared in the earlier examination, PYQ, previous year question, and then refer to model papers. So that will be a good preparation for the board examination.